Now we're going to look at using summations to help us find an estimate of the area under a curve and to find the exact value of that area under a curve. So when we're setting this up, remember when we're making our rectangles, we made partitions, and we can call the most left-hand point x sub 0, then x sub 1, x sub 2, all the way up until we hit x sub n. And let's say we're partitioning these values between some interval a and b. We're going to call c sub k some value that we're going to figure out, some x value in between one of the intervals. And we can denote that interval generically by saying this is the same thing as x sub k minus 1, comma x sub k. So we want to be able to find out, and it depends on which endpoint or midpoint that we're going to use to find the height of that rectangle. If we use the left-hand endpoint to find the c sub k value, you're going to look at x sub k minus 1. So for instance, when I have k equals 0, right, this would be x sub, k starts with 1. K always starts with 1. So if k starts with 1, I have 1 minus 1, which is 0, our first value of our partition, which is the left-hand most. And then if I plug in 2, I get 2 minus 1, which is 1. So that would go in there until I hit n, which is n minus 1. And those are all the left-hand end values of my rectangle. So same sort of idea, if I wanted to get what the right-hand endpoint of each rectangle was, I could find that generically by looking at what x sub k is. Midpoint, I would have to take the x sub k minus 1 plus x sub k and divide it by 2. So the two bounds of my base of my rectangle divided by 2, that would give me the halfway point in that. This one is the easiest one to use. Okay, so remember, we want to find the area of these rectangles. And so delta x, we said, was the bounds of what we're trying to find the area of, in this case, b minus a, all divided by how many rectangles we're trying to get, which is n. So for a right endpoint, if we're starting at a, we're going to add k times delta x. If you want to write it like this instead, delta x, remember, is just b minus a divided by n. So a plus k times b minus a. So we're going to just focus on the right-hand endpoint. But the left-hand endpoint we can do by whatever value we're starting for the bound of our area, a, plus k minus 1 times delta x. Starting at a, so we can write this as k minus 1 times delta x, which is the same thing as b minus a over n. And c sub k, if we're looking at it as a midpoint, starting at a, we have to look at k minus 1/2 delta x, which delta x is the same thing as b minus a over n. Okay, so let's pull up an example to do this. So another thing we can do is, now that we know how to set this up with the height of our rectangle, we can write this as our summation. So we're looking at the summation from k equals 1 to n of our function, the height at our particular x value, depending on if we're using the left endpoint, right endpoint, or midpoint of our partition, times the base of that rectangle delta x sub k. So our example that we're going to look at, let's cut it, is f of x is equal to 1 minus x squared, and we want to look at this over the interval from 0 to 1. The directions say, find the formula for the Riemann sum obtained by dividing the interval AB into n equal subintervals and using the right-hand endpoint of each. Then take the limit of those sums as n goes to infinity to calculate the area under the curve of AB. Okay, so we want to look at this and we want to write out our summation of this when k is 1. Let me move this up. And we're again using the right-hand endpoint. So let's figure out what C sub k is. And let's go back up here. Oops. Where did it go? It's right here, sorry. And let's figure that out. So it's our A value. Our A value in our problem is 0. So it's 0 plus k times delta x. Well, delta x for us is 1 minus 0 all over n. So this is going to be all times 1 over n. So our C sub k value is the same thing as k times 1 over n. Let's look at what f of C sub k is. So f of k divided by n. So we're going into our function f of x, and wherever we see an x, we're going to plug in that k over n. So we get 1 minus, I see an x there, so k divided by n, and that quantity is squared. So let's just simplify it a little bit. 1 minus k squared over n squared. And so that's our f of c sub k. We need to multiply this by our delta c sub k. And our delta x okay, is equal to 1 over n. So now we can write out our summation. We have from k equals 1 to n of f of c sub k, which we said was this. All times delta x sub k, which we said was 1 over n. Okay, so let's look at this. Actually, before we look at the summation, let's manipulate this a little bit so that it's faster to take that summation. And so let's first distribute this 1 over n. If we do this, we get k is equal to, that should be a 1, to n of 1 over n minus k squared. N squared times n is n cubed. We can use our rules of summations and we can break this down. This is the summation of the first minus the summation of the second. where we start at k equals 1 to n. Okay, so this is where you need to recognize that n, that's not the variable that we're using to plug things in. And so we think of that as a constant, and we can actually factor that out and pull it out front. So this is the same thing as 1 over n, the summation k equals 1 to n of 1, minus, so same idea, this k squared over n cubed. I can rewrite this as 1 over n cubed times k squared. And I can pull out that coefficient, because that's just like a constant, 1 over n cubed, k equals 1 to n of k squared. So let's look at the summation, 1 over n. Remember, if we were summing a constant, n times, it was equal to that constant times the number of times we were summing. So this is equal to 1 times n, or n. Minus, we have this 1 over n cubed, and now we have that summation of k equals 1 to k squared. And we had a formula to help us do that, and that was n, whatever we were going to, times n plus 1 times 2n plus 1 all over 6. So it's helpful if we can get this cleaned up a little bit. Let's see. Notice that we have n times 1 over n, that's just 1, minus, here it's helpful if we can FOIL this out, and I'll show you why in a minute, but let's just distribute. I'm going to first distribute n times n plus 1, which is n squared plus n. That is all times 2n plus 1. So if I distribute this out, I get 2n cubed plus n squared plus 2n squared plus n, or 2n cubed plus 3n squared plus n. Okay, so we have minus the numerator, which again we saw was 2n cubed plus 3n squared plus n, once we distributed, all over this n cubed times 6, or 6n cubed. So that was the first piece. Wanted us to find that summation. The second piece wanted us to find that exact area by looking at the limit of this as it goes to infinity. And we're looking at the limit, right? Because we want this n, this is the number of rectangles. We want an infinite number of rectangles. So if we look at n going to infinity of 1 minus 2n cubed plus 3n squared plus n all over 6n cubed. We took that limit as n goes to infinity. Well, unfortunately, and we can break this down as two separate limits. The limit as n goes to infinity of 1 is 1. But notice that we get an indeterminate form when we look at the limit of that quotient. We get infinity over infinity. We can use L'Hopital's rule, but I noticed I would have to do that 3 times, or we can use the rules that we learned at the beginning of the semester. So if we got infinity over infinity, we could look at dividing by the variable to the highest term in the denominator. So we could look at this as the limit as n goes to infinity of 1 minus the limit as n goes to infinity of this 2n cubed divided by n cubed plus 3n squared divided by n cubed plus n over n cubed all over 6n cubed divided by n cubed. So basically right there, we were multiplying this piece by a fancy 1. We were multiplying that piece by 1 over n cubed in the numerator, all over 1 over n cubed in the denominator. That was one of the tricks. So if we simplify now, we get the limit as n goes to infinity of 1, which is 1, minus, well, let's start simplifying. N cubes cancel there. Here, an n squared over an n cubed just leaves us 3 over n. And n over n cubed gives us 1 over n squared. N cubes cancel. So when we look at the limit as n goes to infinity, we have 2 here. Well, this piece 3 over n, that piece as n goes to infinity goes to 0. 1 over n squared as n goes to infinity goes to 0. All over, those canceled. So numerator or denominator go to infinity would just be 6. So 1 minus 2, 6 reduces to 1/3. And so we have 3/3 minus 1/3, which gives us 2/3. So this is actually the exact area underneath that curve that we started with, which was, sorry, where was it? It was way up there. F of x equals 1 minus x squared over the interval of 0, 1. So if we looked at that graph at 1, that's an upside down parabola, but it's just from 0 to 1. You find that area is 2/3. Okay, so next week, we will give you a shortcut so that we don't have to look at this limit as n goes to infinity of the summations of all these rectangles. And that will be called definite integration. We'll do definite integrals.